Okay, let's get right into this. Welcome to this explainer, where we are going to unpack the terrifying yet totally awe-inspiring physics that allow human beings to quite literally build a star on Earth. We're talking, of course, about the hydrogen bomb. Now look, the science behind this is some of the most extreme, complex physics ever achieved by humanity. But don't worry, we're going to break it down so clearly that you'll understand exactly how it works, why it works, and how this single invention completely changed the course of human history.
To really wrap our heads around the massive engineering leap we're talking about here, we first have to grasp the sheer scale of the energy involved. Think back to the atomic bombs of World War II, like the one dropped on Hiroshima. Those weapons were measured in kilotons, which means thousands of tons of TNT. Unbelievably devastating, right? But then we have Cold War-era thermonuclear weapons, like the famous Tsar Bomba. These are measured in megatons, millions of tons of TNT. The Tsar Bomba alone was 50 megatons, so we're talking about weapons that are well over 1,000 times more destructive than those first atomic bombs. The big question is, how on earth did we get 1,000 times more explosive power?
Well, that brings us to Section 1, splitting versus joining atoms.
The core difference really just comes down to fundamental physics. An atomic bomb, or a bomb, relies on a process called fission. Fission is all about tearing things apart. It splits heavy, unstable atoms like uranium or plutonium, and when they break, they release a ton of binding energy. But a hydrogen bomb, or H-bomb, it relies on fusion. Fusion is the exact opposite. It takes incredibly light atoms, specifically isotopes of hydrogen, and smashes them together with so much force that they join into a totally new element. And here's the kicker. That joining process releases vastly more energy than splitting does. In an H-bomb, the massive explosion from a fission bomb is literally just used as a giant match. It's just a trigger to force those light hydrogen atoms together, replicating the exact same process that powers our sun. But as you can imagine, making atoms fuse together here on Earth is incredibly difficult.
Which leads us perfectly into Section 2, the megaton barrier.
Here is the crux of the whole problem. To achieve nuclear fusion, you need temperatures of at least 10 million degrees. 10 million! You are trying to create conditions that normally only exist in the superheated core of a star. Scientists called this the ignition problem. Early on, physicists tried to build what they called the classical super. Their idea was basically just putting hydrogen fuel right next to an exploding atomic bomb. But after 8 solid years of crunching the math, they realized it was a total dead end. At those extreme temperatures, the fuel simply blew itself apart before it could efficiently fuse and release energy. It would just fizzle out.
So put yourself in the shoes of a scientist in the 1940s. You're staring down this ultimate question. How do you safely create, and more importantly, contain a star inside a deliverable bomb casing without it just blowing itself to pieces before the fusion even happens? How do you hold it all together long enough at 10 million degrees? Well, the answer arrived through an absolute masterpiece of engineering that totally reimagined how energy moves.
Enter Section 3, the Teller-Ulam breakthrough.
Let's look at how fast this shifted. Fusion theory actually started way back in 1942, before the very first atomic bomb was even tested. But by 1950, like we talked about, the classical super idea was dead in the water. But then, in 1951, a massive conceptual breakthrough changed everything. Two scientists, Stanislav Ulam and Edward Teller, realized you had to separate the bomb into stages. You couldn't just stick the fuel right next to the atomic trigger. Instead, you had to use the incredible speed of the X-rays coming off the primary atomic blast to physically crush a totally separated secondary target that contained the fusion fuel. It was brilliant. Just 20 months after they proposed this staging idea, in 1952, the world's first successful hydrogen bomb detonated.
To make this staging trick actually work, they used something called a holoram. Think of a holoram as a hollow cavity made of super heavy metal, usually uranium or lead, that completely seals in both the atomic trigger and the fusion fuel. When that primary atomic bomb goes off, it releases about 80% of its energy as X-rays. So you can think of the holoram as the world's most extreme microwave oven. It traps all those X-rays inside, bouncing them around to perfectly and evenly bake the fusion fuel container from every single direction at the exact same time.
But what exactly are they baking inside that oven? Well, early tests actually used liquid hydrogen. But liquid hydrogen has to be kept extremely cold, which meant they needed massive, building-sized refrigerators attached to the bomb. Obviously, you can't exactly drop a giant factory out of an airplane. So they found a genius replacement material called lithium deuteride. It's a dry, solid salt that completely solved the logistics problem because it doesn't need to be kept freezing cold. But here's the coolest part. When the lithium in this solid fuel gets bombarded by neutrons during the explosion, it instantly breaks apart into tritium, which is a highly combustible hydrogen isotope, meaning this dry solid actually breathes its own fusion ingredients right in the middle of the explosion. It's making its own fuel on the fly.
All right, section 4, microseconds to megatons. Let's see how this actually fires.
Let's slow time way down to just a fraction of a microsecond and watch this chain reaction happen. Step 1. The primary fission bomb detonates. Step 2. A blinding flood of thermal X-rays instantly fills the Hohlraum casing. Step 3. Those X-rays are so intense that they actually vaporize the inner plastic lining of the casing into superheated plasma, which crushes the secondary fusion fuel inward with unimaginable force. And finally, Step 4. As that fuel is crushed to thousands of times its normal density, a plutonium spark plug right in the center gets squeezed so hard that it starts undergoing fission too. So you have pressure crushing in from the outside, nuclear fire pushing out from the inside, and boom, the fusion fuel ignites perfectly in the middle.
To give you a mental visual of what this crushing pressure is really like, physicists often describe it as a rocket turned inside out. This compression process is known as radiation implosion. The X-rays heat the outer layer of the fusion fuel container so unbelievably fast that the surface violently boils off or ablates and goes flying outward. And thanks to Newton's third law, every action has an equal and opposite reaction. This surface explosion pushing outward creates a massive, devastating reaction force pushing inward. It literally crushes the fuel like a reversed rocket engine.
Okay, get ready for a huge plot twist. You would naturally think a hydrogen bomb gets all its destructive energy from, well, hydrogen fusion, right? Surprisingly, no. The fusion reaction releases an absolute blizzard of extremely high-energy neutrons, and those neutrons shoot outward and strike the heavy uranium casing of the Hohlraum. In a lot of standard designs, over 80% of the explosive yield and pretty much all of the deadly radioactive fallout actually comes from splitting those uranium atoms at the very end. So the biggest blast comes from fission, not just joining the hydrogen atoms. It is a wildly complex machine.
And that brings us to our final part, section 5, the ultimate limit.
This stage design fundamentally altered the trajectory of global security forever. By using that solid, stable lithium deuteride we talked about, engineers got rid of the giant refrigeration units. Because the fuel was stable, weapons could be safely stored indefinitely in underground silos or on submarines. And most importantly for the Cold War, it allowed for massive miniaturization. The military went from needing heavy, slow-moving bombers to deliver these weapons to having sleek warheads that could fit right onto precision intercontinental ballistic missiles. And the craziest part? Because you can theoretically just keep chaining these secondary stages together, one after another, the explosive yield of a thermonuclear weapon literally has no physical limit.
The physics of the hydrogen bomb represents an absolute pinnacle of human understanding when it comes to material science and thermodynamics. I mean, we figured out how to recreate the core of the sun in a space no larger than a trash can, in a fraction of a microsecond. But understanding this incredible science leaves us with one final, pretty haunting thought to take away. If our engineering now allows for weapons with literally unlimited explosive yield, what is the ultimate limit of human responsibility? Now that we know how to unleash the power of a star, how do we master the responsibility of holding it? Thanks so much for joining me on this explainer. Keep asking big questions and keep learning.